Thanks for coming, everybody. Appreciate the opportunity. Thanks to ACI. Thanks for everybody in the room for being here. I'm really excited to talk about this project. As you saw, it's opened in 2018. We've done this presentation a few times, but not for several years. And back when we were talking about this project prior to and immediately after opening, there were still some sensitive topics about the budget and about the constructability and about the design that I didn't want to hit. But today, now we're 4 years later, I'm gonna share some of those more confidential things with you because the project's in the rearview mirror. It's a big success. It looks like a few of you were in the room for my colleague's presentation over the lunch hour. Nathan, the architect, the lead architect from Allied Works Architecture. And so the idea today, ACI asked us to come with a collaborative complementary presentations about how the project was designed and how the project was executed. So this is the execution portion of that. Start off with a photo, and we'll come back to that at the end. But I work for Turner, as Jeff said, project executive. I've been with Turner Construction. Previous to that, I was with Bechtel, two big GCs and CMs. And this project is special to us for a lot of different reasons that I'll talk about. But just from a pure technical perspective, we don't know of anything anywhere that's been built like this. And I'm going to go into all those details and about how we worked with the design team and our construction team to innovate and pull off this special project. To the ACI folks in the room, thank you. Thanks for having us here. It's certainly an exciting project to talk about, very applicable to the event here. It was all about the concrete for a long time, and we spent a lot of time researching that. That's a big part of what I'm going to talk to you about here today. But I'm born and raised in the community of Central Ohio. Glad to be in Orlando for a couple days. Nice down here, and we snuck away to the beach yesterday. But my friends and family kept saying, "What are you doing down there? Is it a spaceship? Is it a sculpture? What the heck are you guys building?" And it's a sculpture that we turned into a building, and the vision that Allied Works had, we brought to reality. So we're going to talk about how we brought that to reality today. I've already introduced myself, talk a little bit about the purpose and the history of the project and the team that we assembled, dive into more practical things than we talked about at lunch. So how we, from the contractor side, attack the design and look at how to build this thing. And some jobs are obvious, you know, if we're building an office building or even a bridge or something that we've built thousands of times over, we know intrinsically how to do it and what sequence we go through and how to go through that process. But on a project like this, we had to start from square one and think about each step of the construction and how to pull off such an iconic architectural design. So it's a little bit different thought process than we're used to. I'm going to set the context for the project, talk a little bit about the site, civil stuff, but mostly about concrete today, and then just touch on the different unique portions of the project as well. And then most importantly, what we did to innovate to pull this project off and things that are different than other projects because it demanded it of the design. And then we're certainly welcome to take questions at the end, but if you want to stop me, I would welcome that too throughout. So it was a huge honor to be involved in this. Like I told you, I'm born and raised in Columbus, Ohio. I love the area. Alumni of the Ohio State University. I'm an adjunct professor there now. I've worked almost my whole professional career in Columbus, Ohio, and this is right in the middle of downtown, a very prominent site where we built this project. You combine that with a much more important topic that we're honoring the veterans of our nation with this museum. Halfway through the project, it was designated by Congress as the National Veterans Memorial Museum for our whole country to honor the individuals, not a war or a piece of equipment or a certain conflict, but the individuals, the veterans. So for me, I was really honored to lead the team because of my connection with the local area, but then also, you know, what better to inspire a team of people that are doing a project together than we could all think about our dad, our grandfather, or friend who's in the military now and honor them through this project. So just a dream come true to be a part of it. We assembled it, Columbus Downtown Development Corporation, I say not technically, but they're basically the private arm of our city. So I think a lot of large cities have something similar where if you have private and public money into a project, the city can't do it because of the private money. And so Columbus Downtown Development Corporation is the entity in Columbus that bridges those two things, and they pull off some of these in between public-private projects, and that's what we had here. So that was our client. They work closely with a bunch of the visionaries of Central Ohio and pull off these more iconic projects for the downtown community. Turner started as the CM. We kind of morphed into a GC. Pretty interesting delivery method there, which I'll touch on. Allied Works was the prime architect for the building. Nathan Hamilton's in the front row. He just did the presentation at lunch, so I might lean on him a little bit during my talk. Olin was the prime architect for the site design, and then Ralph Applebaum did all the exhibitry design. You can see, wanted to recognize a bunch of different partners that we had on the construction side. I'll pause though and tell a quick story. There's at least a few of my friends and colleagues from Baker in the room. And if you think about the shape of this building and what we were trying to achieve, we're Turner. We're the biggest GC in the country. We did about, I think, 17 billion last year. So we're used to finding subcontractors that are capable and putting a team together for all the projects that we do. On this one, personally, I talked to about 20 different concrete companies and gave them the pitch about how exciting it was to have an opportunity to do this project. And they all evaluated it and looked at the blueprints at the time and basically said, good luck. At least 20 different firms. And so I was on the phone trying to drum up bidders like we always do, but this is a unique effort. And we have a strong relationship with Baker across the country, but also in Ohio. And we kept going back to Mike and his team and begging them to give us a lump sum proposal or a GMP. And they kept being very professional and respectful and said, we've been down this path before. We can't give you a proposal for this project. We'd love to build it with you, but we'll only do it cost plus. And we said at the beginning, well, nobody's going to sign up for that. So we had to keep trying. We actually entered into an agreement with another firm for pre-con. That didn't work out. So one of the interesting things I'll tell you about the delivery method of this project was that my company, Turner, decided our relationship with the client was so important that we hired Baker basically as our self-perform arm and brought them on underneath us. They budgeted the project with us, but we took the financial risk for this unprecedented piece of construction. So our relationship with the client was important enough where I remember back in 2015, my boss and I sat down and we either had to decide, do we tell the client we can't do this job because we can't find the most important contractor to do it, the concrete scope, or do we hire Baker and take the financial risk ourselves? And we decided, and Baker is the most capable in Ohio for sure, if not the country. And we decided to bring Baker on board as a part of our team under our wing and basically hire them to be our self-perform to do this project. So pretty interesting setup. Turner is very risk averse. And we decided in 2015, at least for this project, to throw that idea out the window and take on one of the riskiest things you could ever imagine, especially for a relatively small volume, $50 million job, very, very risky endeavor. So I'd be remiss if I didn't mention these two gentlemen. I called them both and told them I was going to put their names up on the screen here today. Rob Ford was the project manager for Baker and Herb Edwards, the superintendent for Titan Reinforcing. They led the team that did the rebar and concrete. Both amazing, brilliant guys, so smart at what they do. I thank them so much, and we'll mention them throughout. I look for pictures of them. That was the only one I could find where they're hard at work, right? But they pulled it off. We lived in the office complex together for 2 years during this project, and I just wanted to start with that because it's really important to recognize Rob and Herb and all the folks that work for them. Another quick story before I dive in. Somebody mentioned it earlier. We won the AGC Ohio Award in 2018 for the best project in Ohio, which it was a rough job. I mean, there was a year and a half of sleepless nights and thinking we were going to lose millions of dollars. But afterwards, in the rearview mirror, we started to win these awards. I think the design firm did too. And so huge thing. Best project in Ohio that completed in 2018. A big honor from the AGC. We're just beside ourselves and really proud of what we did. And humbled by the recognition. So we entered the national award for AGC. There's 32 categories. We won our category, got invited to Denver, and again, over the moon, so happy to be recognized. We're literally leaving the convention in Denver, the AGC convention, and they take the 32 categories and award them to one main winner for the best project the whole country of the year. We were on our way out the door, my boss and I, and we won the AGC National Award for this project, best project that was completed in the year of the whole country. So the sleepless nights, the concerns about budget, the concerns about reputation, all that was in the rearview mirror. So it's interesting now, 4 years later, to look back on it and just again, humbled, many lessons learned by that, and really lucky and fortunate to be a part of it. And this just reminded us that, you know, you grind it out, you get through that tough project. We may not always win an award, but there's something to be said for getting through it, getting it in the rearview mirror. So moving on here, just a little context. The Franklin County Vets Memorial was there prior to this, which was a concert venue and a convention center. Nathan talked a little bit about this earlier, but an important building to the community. And some people were mad that it was going to be demolished, but pretty tired and it needed to go. So they were looking for something iconic for our city to replace it that really honored the veterans. So when we got involved, the owner decided to do the demo on their own. And this is about constructability. So the site's important. I'm going to tell you a little bit about the site. That was in November of 2015. I'm guessing most of you in the room aren't too familiar with Columbus, but Broad Street is Route 40 that runs all the way across the country. So it's a really important thoroughfare for our city. And back before there were freeways, everybody traveling east-west across the middle part of the country, I think used Route 40. So really important location, and right across from the main downtown, and our downtown's growing to the west. So really important site. We got involved and we helped plan the project, and they built my building. I negotiated $30,000 worth of gravel. They built my building pad for me and helped my budget out a little bit. And we inherited the site, and it looked like this. A couple interesting things that I'll talk about and that affect the concrete construction. We had a levee that was part of our site, which is controlled by the Corps of Engineers, and then a flood wall that was built. This area is called Franklinton, and it had flooded twice, I think, in the past 100 years. So it was important to protect Franklinton from floods, and the Corps of Engineers was responsible for that. There's some facts about the site. It was about a $50 million project, which had a 50,000 square foot museum. The site was equally important. I think for most visitors to the museum, it was a pretty intense experience because they'd be in there maybe thinking about somebody they lost or a certain military conflict. So they complemented the building with the design of the site. And it was really neat to be able to build something with a heavy focus on an iconic building, but also a heavy focus on a really high standard landscape design and implementation. So we got both with this project. Again, relatively small project, but pretty amazing opportunity. Like I told you earlier, public and private funding. There's some benefactors in Columbus that put a lot of money into it. We also had city, county, and state money. So a lot of different money coming from a lot of different places. And we actually, they passed a bill in Congress while we were working on it to designate it as the National Veterans Museum. So the only one that exists is in our city. So important thing here, 2018, we finished open. Thanks to ACI, they were looking for the right project to highlight here. And it's interesting now from the perspective, looking back a few years, to look at the challenges of this project. So a little bit more about the site. We had the levee that I told you about in the red arrow. And then we had the flood wall, which is the blue arrows pointing to. The site architects coordinated with the building architect, Nathan's group, and wanted a view of the city to be part of the building. And so we had to build up the site back here about 15 feet, 50,000 cubic yards or so of soil. But what we realized early on, the original design showed us filling up to the flood wall, which was controlled by the Corps of Engineers. And the Corps told our client, you could submit that. It's a $100,000 application fee. It'll take us a year to review it, and we're probably going to tell you no. So our client made a wise decision. They revised the site design. We ended up building a pretty significant and expensive wall here. But the reason was that the people who inspected that wall needed to have access and see it so that they would protect the area from floods. So that will also impact the way we built the structure, which I'll tell you more about here in a minute. So on the north side of the site, we built this new retaining wall. We left this inspection alley, and then here's the flood wall that then transitions into an earthen levee here. One of the coolest pictures that I've got is from down at the river, just a little bit of visual context for you. But if you're standing at the river looking up the levee, you can see this building kind of creeping out of the architecture, which was part of the intent of the design. But you can tell up on the hill, and the levee was certainly a challenge for us. We weren't supposed to have any equipment, can't interrupt the levee, and that informed how we built it. So fast forward a few months, we got into the civil construction, the foundation construction. We knew this was going to be a challenge. It's hard to overstate. If anybody's worked on a project with a round or radial element in it, it's hard to overstate the complication that introduces. It's just exponential. So we've studied it. We thought we were respectful of the challenge. And as we started building it, we learned we had no idea what we were getting into, is the easiest way to say it. And so that started with the foundations. We had a few hundred auger cast piles, which I'm sure we're all familiar with, and then radial grade beams that varied in width and length and how they intersected with one another. So right away, we knew the first thing we built, even though we were still in the ground, that exponential challenge of the radial design was immediately apparent. For the structural engineers in the room, we also had what I think is relatively unique in a structure that has a torsion element to it. I think normally, at least in my career, in my experience, we don't deal with that. But one of the huge challenges, and you'll see when we get into the reinforcing steel, was that every part of this building, all the way down to bedrock, had to accommodate a torsion in the design, which really complicated things from surely a reinforcing and a formwork perspective. And that translated all the way down because the structural engineers were worried about how these arches would interact with one another and put torsion on the different structural elements of the building. I was telling Mr. Schneider earlier, we teamed up with Baker, as I told you, and they set up shop. They dedicated 3 or 4 of their most seasoned people in their Cincinnati office. And we traveled down there. They set up this war room and this planning room, and they locked themselves in this room for 3 months to figure out how to build this thing. And we went down once a week to check in with them because we were definitely involved in that, and then planning the other parts of the project as well. And what we decided was that we obviously had to break the foundations into sequences, but then we had to decide logistically, how do you reach the building with lifts and cranes? The same thing you think about on every project, but we had a round building and we also had a levee to deal with. So we sequenced the building. Long story short, we started at the levee and we worked our way away from it. So it was a difficult decision to make. Do you start in the middle? Do you work your way out, north to south, left to right? You go through that on every project, but this one was just a little bit more complicated because of the geometry. We also learned that the structural system was not typical. From what we are used to in Central Ohio, maybe you would reinforce the top quarter or third of an auger cast pile. We had to figure out how to put 30 feet of reinforcement into our auger cast piles, again, because of that torsion and the heavy forces that these arches would impose on the foundations. So again, the more we learn, the more respectful we were of this design and what it would take to achieve it. So from our perspective, the design evolution process, Allied Works went through a competition to win this job as the architect. And this is the design that they won with. We call this the concept design. So very early on, when we got hired, this is what we were analyzing. And we were excited about figuring out the challenge, figuring out how to build this. Obviously pretty iconic design, and it was going to be a big feather in our cap to have constructed this building. As we got into it with Nathan and his team, we had to help. It was a very collaborative pre-construction process where we were pushing and pulling on each other, the constructors and the design team, to figure out answers to all these important questions. So early on in the process, it was decided the main material was going to be architectural concrete. It was also the main structural element of the building. So a lot of demands on this concrete frame, architecture and structure. And we had to figure out how to achieve the geometry, how to form the building, how to reinforce the building, what the finish product on the face of the concrete wanted to look like. So these are all the things that we needed to answer during pre-construction. And then from a construction perspective, same questions we ask ourselves on every project, just again, a little bit more intense on this project, where we had to answer all the logistics. What did the mixed design want to look like? We basically created our own with our supplier on this project to handle all the different demands. What formwork system would we use? How are we going to hoist these things into place? What did the budget look like? Long story made short on the budget was that we sat down with our friends at Baker and we said, how do we budget 60-foot tall radial walls that are partially voids because they're arches? And so we did a few months worth of study and we decided we're going to take picture a foundation wall for any building, a flat wall like the wall here. And every concrete company has historical metrics on production and budget and what it takes to build a plane, a wall and a plane. We decided we're going to take that budget and divide the productivity by 12, meaning it's 12 times less productive. And that's what we ran with. You could look at it another way. We took the budget for that wall and multiplied it by 12, the dollar volume. And we said, okay, we think we're really, really conservative, 12 times the normal flat wall. We ended up being we had half the man hours that we needed in the estimate compared to what it costs to build the thing at the end. So it's about 24 times less efficient to build these arches than the best historical data that anybody had could tell us. So almost impossible to estimate, therefore almost impossible to schedule. And there was a lot of demand in pre-con about the finish of the product, the finish of the concrete. What did the face of that concrete want to look like, and what formwork system could achieve that? So the chicken and the egg is, well, does the formwork inform the finish, or does the finish inform the formwork? And how does the budget and the schedule and all the other structural factors affect those things? So there wasn't just one chicken and egg. There's a few of them that were kind of fighting here to help us figure out where this was going to go in design. We all thought board form was beautiful, and I'll show you some slides of how we mocked that up. That was one of the main elements in the primary choice of the design team. We liked the contractors liked the smooth rub or sack finish because we could cover our sins and touch it after we were done stripping. And there was also talk about detractive finish where we'd either sandblast or etch it. That would also give some of that texture. So these are the three primary themes that we are looking at in pre-con. We started off with a bunch of small scale mock-ups as we normally do. But here, when you get into board form, I learned you need to think about the species of the wood and how much chemicals it has in it, do chemical tests, and what type of form oil you're going to use, and how does that react with the wood? How does that react with the mixed design? So we tested all these things as many times as we could. How rough do you cut the wood? What direction is the grain? What species of wood, et cetera, et cetera. And we produced some pretty cool mock-ups. But what we arrived at was you take the 24 times the labor hours I just described, and you add an element into the geometry like board forming. So we told our client, we'll do it. We'll do whatever finish you want. But if you select the board form, you got to take the budget and throw it away, and take the schedule and throw it away, and basically give us a blank check. What do you think the client said? The client laughed at us and said, how about we pick another finish? So after a lot of other tests, which I'll show you in the future here in these slides, the design team decided that the best compromise or the best of all worlds was to select an as cast finish. So basically the intent was the things on the screen. Those of you at an ACI conference probably know an as cast better than me, but the goal was we strip it and we don't touch it, or we don't touch it as much as we can, because that raw quality of the concrete is what was wanted, and it gave you some of those effects of board form, but not that human touch that came with the smooth rub. So those are all the things that we were trying to achieve with an as cast finish. We negotiated every little detail, like, okay, the formwork joints have to align. That sounds easy if you're sitting at your computer writing a design spec. But if you're looking at a 60-foot tall piece of formwork that's going on a radius and you say every joint has to align, well, that gets a little tougher to achieve. So we negotiated, okay, what's the tolerance for that? What's the tolerance? We know we'd have to grind and patch something. All these little details of the specification had to be addressed and negotiated with the client and the design team so that we came up with a plan that everyone would be happy with at the end of the day. The other thing the design team wanted, we had early conversations about white concrete, and we're in Central Ohio, and we knew we'd have to place this concrete throughout multiple seasons over the course of more than a year. And we also knew that achieving a white concrete finish, just the material itself, was likely cost prohibitive. So we decided to go away from the white sand and the white cement and instead add a mineral silicate sealer to the face of the concrete afterwards. That was a whitewash effect. It was semi-transparent, but it tied the color together and eliminated some of the variations. So this is certainly not a plug for Keim, but the product ended up being the right one. And if anybody's into something like this now or in the future, I've given a lot of advice about similar applications and what the right product is. Long story short, my advice is if you're working on an exposed concrete project, this type of sealer is a great solution. The more you can test it early on, even with small samples or even 1 by 1 or 2 by 2 samples, I think you could find the right product. In our case, Keim ended up working out. So you can see there, the finish is a little bit whiter. I think we used like a 10 parts to 1 dilution, so diluted it a lot. Still had the characteristics of concrete, but added a consistent monolithic white look to the face. So you can see the difference there in the end product. It pulled it all together pretty beautifully and gave a lot of credit to the design team for having that vision to know, okay, we like the raw concrete, but it's got to be brought together somehow with the color. So now I'm going to rewind that you've seen the finished product, and we're talk about how we achieved it. Starting with schematic design, the original schematic design, you may not be able to read that, but it says this is a 5-inch steel plate structural ring. So the original design was a structural steel box beam that there were talks about post-reinforcing, or post-tensioning. So we started diving into that, and we said, well, wait a minute, I don't think anybody's heard of post-tension steel box beams. And we reached out to 10 different fabricators, and they basically told us there's no way this thing's ever going to be built because there's no way anybody could ever afford it. And the first estimate we did for the steel, we realized the frame was going to be more expensive than the budget for the entire project. So we worked with Allied Works, and they pivoted, and I think they were headed towards concrete at that time anyways. And we came up with this arch section that is reinforced concrete. And this is a good story about, I think, an effective value engineering process. We all know that term, and there's a stigma that goes along with it that VE is oftentimes necessary, but I think on the design side looked at as a negative from time to time. So this, I've told this story before specific to VE, but these are the arches of the building, which I'll show you more of the geometry later. But we had these long spanning arches that are compound curves. So you look at them in plan and they're curved, and you look at them in elevation, they're curved. So that's what we were trying to achieve. And if you take a section of one of those arches, the original design development drawings showed this double chamfer and the sharp ends. So it scared us a lot. And we said, let's talk about that a little bit more, because we have a multi-thousand-pound rebar cage that needs to rest on something before it's poured. And that slope is concerning. We also have sharp edges, which I think is a no-no pretty much anywhere in concrete, right? So it was a good start, but we wanted to improve on it. So then we went to like a DD2, a second DD, we called them the GMP set for pricing here. And we talked the team into clipping off the sharp edges. We had a little bit more information on the reinforcing design. And we learned at this time that the stirrups had to be completely closed. We thought it was going to be a great idea to put 2 nesting stirrups together to build this rebar. But if you put torsion into a design, the code said it has to be completely closed stirrup. So I'll explain later why that was such a big challenge. But the arches changed, varied in width as you went up and down in the arch. So there was no consistent stirrup dimension. Depending on which stirrup you looked at over the section of this arch, it was an ever-changing dimension. The other thing was there are no expansion joints within the arches themselves. So the cracking was a concern. We had a lot of discussions about control cracks, control joints and construction joints, and how those were handled. And the long story short was the decision, and I'm paraphrasing here, but the decision was we're just going to put as much reinforcing in it as we can. And that's how we're going to control the cracking. So we asked the structural engineer many times, how much of this rebar is structural and how much is for crack control? And they basically told us every time, we don't know. Just keep going. There's enough for both. So really heavy reinforcing, which I'll show you some photos of here in a moment. And so this is what we arrived at in the construction documents. We were successful through some arm wrestling to get rid of that bottom chamfer. And we kept this top chamfer with the sharp edge cut off, which ended up being really beautiful, hard to achieve, but really beautiful. And you can see one of these sweeping curves here where our formwork had to obviously form that shape. And we achieved that profile throughout all the primary arches on the project. So it's one of many good stories about how we got to a point where it could be affordable, it could be buildable, but also achieve the intent of the design. It was really important to the design team to have some of these elements of the section in the geometry. So we convinced our client that it was worth about $300,000 to invest in a large scale mock-up before we made mistakes on the main structure. So we wanted to learn and make the mistakes on something that was not implemented into the permanent structure, which again, mock-ups is something we do on every project, but I would guess on most of our jobs, we don't invest that type of money into a large scale mock-up. But the construction of this thing was just so much different than we were used to that it ended up being a great investment. This is an example of where 2 arches would intersect in our superstructure. And we decided to build this as the large scale mock-up. And we really learned a ton from it, which I'm going to take you through here. One of the hardest parts, and I got a little discouraged when I kept calling people and asking them to participate in the project, and they kept saying, good luck, no thanks, right? And one of the second effort of that after the concrete itself was that we realized for all the voids, all the space underneath and within the arches, we needed to form those somehow. Of course, that's obvious, but how you do it is a little bit tougher question to answer. So we had what we called void forms or box outs that we use on every job, right? If you have a pipe or a duct going through a concrete wall, you box it out with a rectangle, no big deal. But what we realized about these was that they're on a radius and they have shapes like this and that chamfer I talked about and the notch of the arches where they intersect. So we had to find people who specialized in plywood construction and who had the capabilities to model in 3 dimensions and then produce individual files that they could then put into a CNC machine to cut out all these waffles to the exact shape and piece them together. So each one of these box outs was thousands of dollars. We used it once for that location, ripped it out with crowbars and put it in the trash. So we had to go on this mission of finding companies that would build box outs for us as a part of our concrete team. We ended up having 4 different companies that did nothing but box outs, and they had the technical expertise in the modeling software and the CNC process and carpentry to produce these things. So this is something, rebar formwork box outs. We were always dying to get on site. It was just so hard to get through that design process. Something that we learned from the mock-up for sure. We had names for all of them. That I think was the shark fin and the crotch and on and on. So there's one drawing that each box out had a set of shop drawings on its own. This thing was maybe 6 feet wide. And this is just the overall shop drawing. So every box out had its own set of shops. And we also realized that the concrete would make these want to float. So we've dealt with float elsewhere, of course, but the challenge of this and the mock-up was a good one, a good example. When you're pouring this section of the mock-up, this box out wants to float. But then when you're pouring this section of the mock-up, there's a lot of gravity load on that section of the box outs. So we had to come up with a box out design that would hold it both from floating and from deflecting down under the weight of the concrete. So a lot of pretty extreme engineering into something that you normally wouldn't even think about. You have a carpenter go build a rectangle box, slap it in the formwork and move on with life. A couple other interesting things. We tested out guillotine ports. We ended up pumping the concrete in from the bottom of the formwork and progressively getting higher as we went. Tell you more about that in a minute. Some pretty heavy duty formwork accessories that are standard accessories, but applied in a different way here on this project. And then we had to deal with the geometry of this building. And we selected Perry, who's one of the largest, most capable formwork companies in the world. And they did a pretty tremendous job for us. What they came up with was that they used their standard girder system much closer together because of our mixed design, but a tapering shim. So that may be 1/8 to 1/2 to 3/4 to 1.5 inch shim, if you could see them in there. And that's how we achieved the curvature of the building. And so every piece of formwork was unique, and we'd use it once for that spot, and then we'd take it down, tear it apart back to the girders and send it back to the shop, the formwork shop in Chicago, rebuild it for the next area, totally unique design. And we were constantly shipping formwork components back and forth. So typically you use formwork because it's repetitive and you can reuse it on the flat section of wall and the next flat section of wall, right? But on this structure, every piece of formwork was unique in its radius, its height, its width, and how we lined up all those control joints. So pretty amazing feat that the Perry engineers pulled off here to bring this to reality for us. And then 2 layers of plywood to deal with the structure, the pressure of the mixed design, but then also we used the HDO face to pull off that as cast. Anybody heard of the term NURBS? Yeah? Oh, the other architect in the room, a couple of us. Yeah, there's the definition. You can read it. I'll screw it up if I read it to you. What we realized was that there were 3 primary rings. This is number 1, the outer ring, the middle ring, and the inner ring. By the way, that's a 3D model of just the concrete superstructure. And there's no, what we realized when this term was brought up, there was no radii. It's an ever-changing radii. So we couldn't strike a point and pull a radius. It was an ever-changing radius. And the way this was designed was with this NURBS concept, and others in the room can probably speak more in a more educated way about it. But the base design was done in rhinoceros, which I guess is more able to handle complex curves and complex shapes. And so we had to convert that into AutoCAD 3D and able to implement it and able to be able to implement it. But again, we kept learning more and more about this project and talking about what radiuses were the same and what radiuses were different. And early on, we realized none of the radiuses were the same. They all changed. So therefore, we had to incorporate a formwork budget that had unique formwork in every part of the structure. So the mock-up, we started that process. We started with a MDO plywood, which didn't work out because it left the tiger striping on the finish, but we were figuring things out as we went. You could see the shape of that mock-up start to come together. So really expensive false work here. You could see the whalers or the braces where we could tie the formwork down and tie it from floating at the same time. Tie it down, tie it up. And then we started learning about what the reinforcing looked like, how to put this thing together. We had to be very mindful about which side of the formwork we stood up first and which side was the close-up side, because it mattered a lot to what the outside of this building looked like and that finish that we were trying to achieve. We learned, and somebody in the room might correct me here, but at the time, there wasn't a reinforcing detailing company that was capable of doing this whole project in 3 dimensions. All the reinforcing detailers basically said, "You're crazy. That's not how our industry works. We design in 2 dimensions." But we realized here that with these sweeping curves, even with the dowels, this is a shop drawing of the dowels coming out of the foundation. That curve was strong enough that the dowels sticking out would interrupt the formwork and hit the formwork. So we had to figure out how to resolve every little thing. Like 6-foot dowels, we needed 6-foot development length. So how do you do that with straight bars? Because you're not going to detail every single piece of rebar coming out of your foundation to the exact radius or NURB that you need in that location. Back to the statement about some of the rebar is structural and some of the rebar is for crack control. And there's other reasons we need rebar. But what we ended up with was number 8s through 11s longitudinally at 4 inches on center, and number 5 stirrups at 4 inches on center. So we basically, you couldn't even get a couple fingers in between them. And we had to build these shapes out of rebar to achieve the structural design. You could see the closed stirrups I mentioned here. We had this great idea to nest the 2 stirrups together to deal with that gradation in the width, but you couldn't do that with a closed stirrup. So we had to make every single one unique to its location and figure out how to weave it all together. The other thing I'll mention here is that our mock-up was where a representation of where 2 arches cross each other. 2 arches. Yes, sir.
So Nigel, I just got a quick question. If you go back to the other slide. So when you look at those bends for those stirrups, did you guys have to use like heavier, tighter tolerances with the stirrups in terms of what you were getting from the fab shop and it fitting specifically in your formwork?
Yeah, the tolerances were high. Luckily, because of the architectural concrete, I think it was 2 inches of cover was specified. So instead of a normal maybe 1 or 1.5 inches of cover, we had 2. So that gave us, relatively speaking, a little bit more tolerance. But all the rebar had to be bent off site and to about a 1/2 inch of tolerance. And you're talking anywhere from 10 to 20 foot tall stirrups that you had to get within 1/2 inch, which is, I think, a little tighter than we're used to with reinforcing steel.
And in order to protect schedule, I mean, what would happen if one of those bars was missing? Was there a field bend process that you had?
Yeah, but pretty complicated shape. So we came up with a process to bend on site, but obviously tried to avoid it wherever we could.
Okay. And with that, if we could take a quick pause to just show the PDH numbers for the session, please.
Thanks, Jeff. Anybody else while we're waiting? No, they had the double hook. So they had to be, I don't know the right structural engineer term, but the hooks had to be
135s.
There you go. 135 on both sides. So you couldn't slip them together like we wanted.
Yeah. So if anyone in the crowd has any questions, if you could please approach the mic because we're recording the session And there's our PDH codes for the midpoint. All right. Go ahead.
What was the maximum size of the aggregates?
We ended up at 3/8 max. And I have a shot of the mixed design summary here in a minute. But 3/8 max is the answer to your question. Apparently, the gentleman who asked about the closed stirrups, if you have torsion in a structure, apparently the structural code says you have to have a closed stirrup. And we tried to fight that like 10 times and we didn't win. Yeah, hard to change the code, right? We said, no, that can't be what it says. We good? Where was I? Oh, so the arches either crossed in the same plane or they crossed in front of behind one another. So we call them an in-plane crossing, which is an X, or an out-of-plane crossing, which they would pass in front and behind of one another. Both were wildly complex and hard to wrap your head around, but we learned that the out-of-plane crossing was just almost impossible to build. But our mock-up was an in-plane crossing, so we had a cross where the 4-inch center longitudinal number 9s would cross another set of 4-inch number 9s, and then the stirrups around the whole thing. So that's what we tested in the mock-up here. And the other thing, back to Herb, and brilliant, Herb's a 35-year iron worker. He's now a consultant for Baker. Just a brilliant, brilliant guy. And what we realized was that if Herb's guys were 20 or 40 or 60 feet above the air, taking number 9s and shoving them into the formwork, they're probably 200 or 300 pounds a piece, each piece of rebar. And you can't do that at any height in a safe way. So what Herb said, and he was adamant about it from the beginning, is we have to come up with a way to prefab the rebar on the ground in the right shape and pick it up and put it in the forms. And everybody told him he was crazy, but we couldn't come up with a better answer. So we tried it on the mock-up, and Herb had his surveyor lay it out on the parking lot on the ground. And then we built inside the lines like you color in elementary school, right? And then we picked the thing up, the mock-up, I think that was 10 or 12,000 pounds. So a lot of weight, but not huge for a crane pick. And it taught us a bunch of things. So we plugged it into the formwork. We realized, back to Jeff's question, how tight our tolerances needed to be, not only with the reinforcing fabrication, but also with the reinforcing installation. So when we're building these shapes, we had to be well under an inch of tolerance, or else we couldn't fit it in the formwork. And then we had to figure out how to splice structurally onto everything sticking out of the foundation or into the adjacent pour. So as the mock-up process continued, we just kept learning and learning, and it was pretty effective. We learned how to build bulkheads. Everybody in the concrete industry says, yeah, bulkheads 101 concrete construction, right? But not in this type of shape, in this type of formwork, with this type of reinforcing. So we had to rethink our bulkheads. We had to rethink how we splice rebar. You can see in this photo, if you look down from end to end, it's a real gradual curve, but that just sets us up for a bunch of additional challenges. We had to come up with shoring designs that would hold the boxes in the right place, not only from the uplift and the down pressure, but also against one another. So there's the mock-up all buttoned up. There was a big achievement to get to that point. And then we started pouring it, and we decided, because all the arches are capped at the top and the rebar was so dense, there was no way to place it conventionally from the top. So, yeah. Yeah, we went through all the normal, I would assume, or normal trial and error with taper ties and pencil ties. We ended up using a conventional, I think they're 3/4 inch steel ties. So nothing too crazy there, but it was the best application for this. And you can see them all. And I think probably a lot of experts in the room. You also see the whalers are a lot more closely spaced than you would anticipate on a normal wall, as are the vertical girders there. So that's due to the form pressure and more congested form ties too. So our carpenters And our iron workers were always fighting that throughout, because once we put the rebar in, you'd have to shift it around to get the ties through, right? And the embeds. So what we decided here, because of the demand on the finish, because the formwork is capped to achieve the geometry, and because the rebar is so dense, we couldn't pour from the top with a tremie, couldn't get a tremie down into that cage. So this was the first time we tested on this project. The guillotine port I mentioned earlier, we plugged the pump truck in, and it progressively went up to the next guillotine ports as we went. And we actually tested in place the formwork pressure for the mock-up and the first, I think, 5 or 6 pours on the main structure. Because typically, and again, I'm sure most of you do this for a living, but typically formwork pressures are theoretical. And you know from historical data, this mixed design and this type of formwork will result in this type of pressure. And you got to pour it at a speed that lets it cure before the pressure becomes too much. But we had self-consolidating concrete on this project, which I'll get to in a moment. And we had to pour it fast enough so that it wouldn't set up, because it had to be a monolithic pour until we got to the construction joint. So we had to have that balance of pouring it fast enough so it wouldn't set up, because you're pumping through what you had previously pumped, because it fills up the form. But we couldn't pour it too fast, or else we'd blow the balloon. In order to achieve the as cast, it had to be basically almost cabinet grade construction, and it couldn't leak, or you'd have problems with the liquid coming out of the mix, right? So we thought it was really important. Those are pressure gauges there. So we actually tested the pressure for the first half dozen pours. So we weren't working on theory. We were working on exactly the known pressure that all these different variables brought together. So we learned some things, like we couldn't fill up that tip with the first pour, and the architecture team would not like it if we had this weird little shape. So that was the bulkhead was here. We had to fill up all the way to the top, and we weren't set up to do that on the mock-up because we didn't know that was going to be a problem. So we filled it up with the next pour, but that doesn't look great. So we had to deal with, okay, we got to fill this void up completely, and we have to look at the highest points in elevation and make sure we know how to get concrete in there. Baker, Rob specifically, and Herb did a great job. After this process, me and Herb and Rob brought everybody into a room that worked on it, all the foremen, all the tradespeople, and said, we got to maximize on this investment of the mock-up. What are the plus and what are the deltas? What did we do right? What could we have done better? And so we wrote all these things down and incorporated them into the rest of the project, and really got the maximum benefit out of this mock-up. And it's funny, we were super proud of the mock-up, right? And we hadn't even started the project, but there it was. We're like, all right, we're going home. And then we realized, no, you got to actually build the building. Anybody heard of Maxim Cranes? Is Maxim around on the southeast here? We almost sold this to them. I'm not kidding, because it almost exactly matches their logo. So fast forward 2 years, we had to knock this mock-up down because it wasn't supposed to go there. But it was a shame to knock it down. And Maxim I said, you could have it. Forget buy it, you could have it. But they couldn't figure out how to transport it to their headquarters, so we ended up tearing it down. But you can see some of the features we're talking about. We tested out an embed, which I'll get to. Really tough to put embeds in the structure. But you can see a construction joint here and here. We tested a bunch of different plywood. We tested form tie patches and patch material. We ended up testing 40 different colors of tie hole patch material so that we could get it to blend in. You can see the chamfer we spoke about on the top of the arch and that smooth curve.
So Nigel, I got 2 questions for you. One is, was there any special curing requirements in order to get that look? And second question is, did you use anything special in terms of controlling your dimensions and your lines and grades and elevations, right? Because it's really hard to achieve that shape.
Yeah, great question. So curing, we were lucky. We cured it like a normal wall. We left the formwork on for, I think it was 5 days, and we got the cure that we needed through that, which is pretty typical process. And I'm going to get into the line and grade here in a minute, Jeff. So really another thing we learned that was really important is this layout and surveying methods that we are used to could not be employed on this job. We had to really take it to the next level. And that's one of the innovations that I'm going to talk about here in a minute. So you can see tiger striping problems, little bit of consolidation problems where we had some formwork leaks, figuring out the embeds, the form ties we talked about, aligning the joints. We had a lot of talks about screw head marks and how to deal with that. So every little thing we analyzed on this mock-up. So out of the Baker, yeah, Mike.
Yeah, can you hear me back there? Okay, so there's a couple other things in the mock-up. You had mentioned those dowels, and if you
Yeah.
look at one picture, we had about 10 slides back. Our dowels didn't line up to be able to, that, I think that's on that green.
Yeah,
That was one of the lessons learned, is we had to do something different on the dowels. The other is the dimensions that we had to work within. If I remember right, it's supposed to be about an 1/8 inch, I think, on the tolerances. And so a lot of people here do formwork. Think of those things 60 foot in the air, all those boxes, the precise corners that have to be there, and we had to be within an 1/8 inch. So, and at the time, because we weren't sure what the finish was, we were still trying to decide or define what it was going to be. We had to work under the premise that there was absolutely no grinding permitted. So we had to get it right the first time, because that was the premise that all of us worked on to start.
thank you, Mike. So that's what we ended up with. Lots of things learned, lots of things that we could improve. What came out of Baker's team's war room, where we were hand in hand trying to figure out how to build this, was 49 pours for the superstructure. So every color represents a pour, but it was so difficult because the way to break it up, normally what do you work on? Third points of a structure where you put your bulkhead. None of the traditional rules applied. So we had to figure out the intersection between every color was a bulkhead and a construction joint. And we had to figure out exactly where to place those. And then how does the formwork play into that? How does the rebar play into that? Does the rebar or the shoring want to drive those decisions? Is there something else that wants to drive those decisions? Can you even put a bulkhead there? All these things, every single line had to be analyzed how we phase this project. And then we had to look at the site. I told you about the levee because we had to figure out logistically, how do you get people and equipment to each pour to build this building? So we had a foundation phasing, we had a superstructure phasing, and what we decided was it's hard to see with overhead shots. That's why I showed you the photo looking up from the river. We're going to work our way away from the levee. We aren't supposed to have any equipment up here. So what we decided is we're going to build our way towards the parking lot, out east to west. And we also started on, relatively speaking, some of the simplest walls, which were foundation walls, but still had the geometry challenges to them. So we got about halfway through this outer ring and we're about 3 or 4 months behind schedule. So we thought it would take 3 months. It took us 6 months. And we had to come up with a way to try and fix that. So time is money, right? So we convinced ourselves that we'd build that third innermost ring at the same time as we were backing our way towards the parking lot. So we moved some things around in the sequence to try and pick up some time. So half the outer ring, then we did the middle ring. We had built the inner ring, which was a challenge in itself. And then we started closing up the middle ring and the outer ring, all from the levee out, which was based on, if you look at the crane, the primary crane, we had a few, and then the man lifts that were required to get to the formwork, we had to base our logistics off of backing your way out. Well, you still had access for all the equipment. And it was a pretty brilliant decision that Rob and the Baker team made.
So Nigel, I got a question with that middle ring. So what do all those formwork braces connect to at the center of that middle ring?
We had to place a sacrificial slab basically that had the structural capacity, and then it was just abandoned, but we kicked them off down to a sacrificial slab. So working our way out, we started structural steel. Every piece of this thing was planned in advance, much more heavily than normal planning efforts. More advancement in the process. So east to west, away from the city, was the general sequence of events. So circling back to the mix design, there are a lot of different factors on it. Obviously the structure, I would say, was number one, but the strength of the structure, but closely followed by the demands of the as cast finish. And then how do you actually build it? So your question about the aggregate, we decided due to the congestion of the rebar, it needed to be 3/8 max. I think typically in Central Ohio, we would use 3/4 max mixed design, but we stepped that down here. I'm sure there's mixed designers in the room. So we partnered with Anderson Concrete, who's, I'll plug, the best ready mix that we have in Ohio. I've worked on 3 really unique concrete projects with them, and they responded here. Our strength was 6,000, our design strength. Every break broke between 10 and 15,000 at 28 days. So Anderson was so respectful of this project, they knew we didn't want to talk about removing any concrete arches. So they over-designed this thing, and we started breaking them. We said, "You guys know what happened here?" And they said, "Yeah, we are a little bit more conservative than we told you." If you're familiar with SCC, it was a learning curve for us, but instead of a cone test, you do the spread test, right? So you flip the concrete cone upside down as a funnel, and you pour it full of self-consolidating concrete. You lift it up, you measure the spread on a diameter. So not anything our team had ever seen in the past. The Baker guys had a few times, but this mix was unique to this job. You could see water reducer, super plasticizer, a stabilizer. It had to balance we had to balance this mix where it had to flow throughout the whole formwork extents, but it couldn't desegregate, right? Or it couldn't segregate. So we had to add all these admixtures and trial and error to make sure that it could flow enough, but it wouldn't come apart when it was trying to do all the things that we demanded of it. So lots and lots of chemicals, but we got it all dialed in exactly. And it had the structural properties, it had the aesthetic properties that everybody demanded out of the project.
So did it require any vibration, external vibrations?
So we couldn't, just like we couldn't pour with a Tremie, we couldn't stick a traditional vibrating tool into it. So we tried, I don't know if I have a photo of it. We tried to clamp on form vibrators, and they didn't make much of a difference. So we ended up going with a limited vibrating and relying on the mix to consolidate itself.
So question, what was the maximum pour height with the SCC?
I think we got up to 30 or 35 feet, but again, it wouldn't set up at the bottom. By the time we were up, it was not like a typical wall pour where, after a certain amount of time it would set up.
Everything was designed for full liquid head. That was part of the reason for the monitors, which you can see at the top of your picture.
So we went 30 feet, and like Mike said, at the bottom, you planned on it being liquid just to be as conservative as you could. And throughout the first 6 pours, you can imagine every 30 seconds, everybody's asking, what's the pressure? What's the pressure? What's the pressure? And we're constantly monitoring the pressure to make sure that we know what it is. Bakers, some of the Baker guys, I think Wes had it on his computer. Their joke was, we pump hard. And we changed it on this project to, we pump very slowly and carefully, right? Because this is not the type of thing. I mean, we're blowing up a balloon, right? That's what it is. It's a closed formwork. We had to caulk the joints in the formwork. So we're literally blowing up a balloon. And if you let that get out of control, the whole thing will pop. Yeah.
The measured pressures, was it calculated always conservative?
That's a great question. I don't remember exactly, but I think we were never more than like 50 or 60% of the theoretical. So all these factors of safety we put on the calculations, it showed us that we were well under them, which gave us the confidence. We had planned on putting the pressure gauges on every pour, but we got enough confidence from the first 6 pours that we knew we would never get close to what the formwork was designed for. So pressure monitors, spread test, I'll tell you a little bit more in a minute about how we injected the concrete. So we kept learning about this project and becoming ever more respectful of the challenge. what we learned while we were designing the formwork was that there's no dimensions on the drawings. And if you think back to this ever-changing radii, there's really no point if you had a tape measure where you could start and end your measurement. So back to the question earlier about line and grade, we had to figure out how to overcome this challenge with no dimensions on the drawings and figure out how to build this really complicated structure. So there's a couple renderings. We imposed our 49 pore plan onto our 3D model so that we could visualize it. We actually 3D printed a model of this building because as we started building the foundations, we were looking at the 2Ds and we said, man, these 2D blueprints aren't telling us what we need to know. So then we started to rely on the computer model as we do on most projects nowadays, but even the computer model wouldn't tell us what we needed to know. So we printed a 3D print of the building and put it on our conference table, and the combination of the 2D plans, the 3D computer model and the 3D print, we were able to point and analyze things completely and have the full picture in our head before we started the shop drawings and for sure before we started building it. So I won't bore you with flow charts here, but this is an important one here because what we realized was 2D submittals for that structure wouldn't work. So we worked with Nathan and the Allied Works team to come up with a process where we used 3D submittals and we came up with a legal process blessed by our attorneys between design, construction, and owner that would allow us to take the design model, which I'll say was pretty close but not detailed enough to build from. And we broke that down into groups of pores, and our detailers would then refine that model to the point where we could use it for line and grade. And then we'd take this section of 6 pores and call it section A, and we'd submit it back to the design team as a 3D computer file, not a 2D shop drawing. And the design team would overlay it on the base design model and then give us the thumbs up or the thumbs down that we had detailed it accurately and it's still overlaid on their model, but we could move forward. And so that's what this process says, is that we would do 3D submittals. And we came up with this, which I remember the meeting with Allied Works lawyers where we convinced them that this was necessary. And so when they stamped the submittal approved, they're saying that we could use it to build the geometry of the building. So we literally built off the designer's model that we developed more, which I know there's tons of talk in the industry now about the liabilities and how you go about that. On my current project, we're still having those conversations, much different geometry, but this is kind of a pretty innovative thing, both legally and constructability wise, of how we achieved the challenge of not being able to represent what we were going to build with a 2D shop drawing.
Has anybody talked to you about this?
Yeah, I've given lots of people input on different projects, but if anybody's interested, I think we're sharing this presentation and be happy to talk to you about how we implemented it, because it was pretty simple once we got down to it. And what the attorneys, we had our attorney and the designer's attorney, who said, the designer's attorney said, we would never give you our model to build from, right? I think we've all probably encountered something like that. And what we said was, well, the contract documents won't allow us to build it. We can't get the information we need out of them. And the design attorney said, oh, I didn't know that. Well, then, yeah, you got to build from the model. And so it ended up being a pretty simple conversation because we had to get the information necessary to build the project.
So
Yeah.
you mentioned you tried detailing rebar in 3D. Did you end up doing that?
No, we convinced ourselves that the natural curve of the length of the bar would satisfy the curve of the building. So only for the tightest areas, we bent that, but it had to be bent to a constant radius. So luckily the bar at 20 or 30 foot lengths was flexible enough that we bent the tightest stuff, but the rest of it was straight and it was able to be kind of forced into the formwork. Yeah.
Did you consider steel fibers that you have to bend rebar and all that bends and rebar?
Yeah. Yeah. But if you go back, I didn't do any of the structural calcs, but if you go back to these arches, some of them are 250 feet spans, but then they also lean out 50 feet or more. So just the structural demand didn't really allow for fibers to play a big role in the reinforcing design. Thank you for the question. So this is one big innovation which led to how we laid the building out. After every pour or group of pours, we would 3D scan. And as you can imagine, our curtain wall fabricator, which I'll get to in a moment, was very concerned that the concrete had to be in the right spot. So we had about a quarter to a half-inch tolerance to the face of the concrete, or else our curtain wall, which was worth a few $1,000,000, wouldn't fit. So these are the heat maps of how far in or out of tolerance we were with the face of the concrete. These shop drawings for the formwork from Perry were just insanely complex. These are model shots that we had to put on the shop drawings so you could even understand what you were looking at on the formwork drawings. Weird little spots where arches crossed, all kinds of little things that we, again, had to find somebody to build out of plywood. I like these shops just because they're different sections through the intersecting arches. So it's hard to even wrap your head around what the heck we're looking at. But if you go, that's right where the two arches pass each other. This is one arch and this is the other arch out of plane with each other. And as they converge, you have these really complicated formwork platforms. The white is the concrete, and the green and the red is the box out shapes. So you can see throughout all these sections, that's the same pour, but our box outs change shapes as you progress through this intersection of the arches.
And the different colors show which one had to be set first. I
Right.
think it's the green was set first and the red had to be set second in order to accommodate it.
Right. And the rebar guys wanted to dictate the process, and the formwork guys wanted to dictate the process, but we had to figure out how to do what Mike said and sequence it in the right way. Kevin McGuire, is that right?
Yeah.
I haven't worked with Kevin in a few years, but Baker's modeler came up with a brilliant way to represent layout drawings, which is not an innovation in itself, but the way that we developed as a team with the architecture team to communicate what we were going to build really ended up being pretty innovative. So we'd have isometrics here. The blue was the pour in question. All those are embeds, the little black dots. There's a plan view, special sections that would communicate different shapes. I made every trade sign off of these because I didn't want anybody coming back in the future saying they didn't understand where their box out or where their sleeve went. So all our primary contracts signed off on every concrete shop drawing, which is an important part of the process. Baker's drafting team also, at our request, figured out how to capture the finish, whether it was behind a drywall wall, we didn't care about the finish, or it was at the front door of the building and we really cared about the finish. We also represented that with the different textures on the drawings. Every embedded item is captured up here with its quantities, including how much concrete you have to order. These are all the embeds with piece marks. And then back to Jeff's question, and back to the 3D submittals, we work closely with Nathan's team to identify points to verify that we are at the right coordinates, the X, Y, and a Z, so that we would lay this out, our surveying team would lay this out in the right way. So that's a table, and every data point for every embed and every stop of the pour, and we had subsets of points along every arch. And then what we did in the submittal process is we highlighted maybe a half or a third of them, and we asked for a verification from the design team, which re-verified the 3D submittal that we are laying this building out with the right coordinates. So we went to great lengths to make sure in the virtual world we were coordinated, and then we had to figure out how to translate that into the physical world, which our lead surveyor, Bubba Watson, fantastic guy, brilliant surveyor. So he took this stuff and he ran with it in the field, but much more complicated than laying out a single plane wall. There's an elevation of one of our pours. So box outs, embeds. That was a relatively simple pour because all we had was door openings, but still you can see it's just cluttered with stuff.
Question on that. So if you want to wrap it and lay it out flat plane or protect it?
Yeah, great question. We learned this from Allied. They called them unrolled elevations. So a normal building, you look at it in elevation, but that didn't work on this building. So we had to unroll them, slice it and unroll it, which skewed the dimensions a little bit. But that was the only way you could really communicate it in 2D. So a few things branching outside of the concrete itself, the embeds here, each one of these plates is an embed where we'd weld a shear tab on and attach a beam to. This is the same pour. You can see the 3 door openings, That's the innermost tight radii ring. And all these embeds we learned were going to be a huge challenge. The Nelson studs have to fit in the rebar. Depending on which face of the formwork you stood up first and attached second, the embeds were a big challenge. So at one point, standing on the levee, that's what our project looked like. And you could see the one arch here, another arch here, and then the next one taking off over here. So pretty incredible engineering feat from formwork designers.
That question about the spaceship building gets a lot more legitimate.
Right? Yeah. Yeah. Pretty wild. I'm glad it's 2022 and not 2017.
Each of those braces that are there weighed 700 plus pounds.
Yeah.
So again, it wouldn't just depart was also up the turnbuckle.
That's the heaviest kicker that Perry has, and we needed hundreds of them. So there's more complexity. You can see these. This is where 2 arches were diverging from each other, and that's a box. That's a false work box. These are all false work boxes. So the critical path was of the schedule, and I'm a construction scheduling nerd, but the critical path is obviously the concrete. But then within that ended up being the formwork, and within that ended up being these void form box outs. So that's why we put so much focus on getting these void forms engineered, because we realized, which we hadn't realized when we started the project, that these void forms were the most complicated part of the whole thing, which you see here.
Nigel, did you have to hammer your whalers there, or did you shims on each point? How did you
They're shimmed.
shim?
Yeah, we used as many typical Perry pieces as we could, which the whalers and girders were typical, but everything outboard of that was shimmed, and everything inboard, like here in these voids I think you're talking about, was shimmed as well. Yeah. Sir?
I just had a question about the end, but some of the pictures show that they're quite long. Did you have to radius those to match? You know, all different?
We went back and forth about that, and we decided to let the cream get behind them and chip it out. But there were pros and cons to that, which I'll show you in just a minute. These few shots are just speaking to the complexity of the formwork. Again, an out of plane crossing where the arches are in front and behind one another. So getting people up to the pour obviously was a big logistical challenge. There's one of my favorites. So that's 60 feet tall. That's the stand-up side of the formwork. Obviously, we hadn't started putting the rebar in it. We have the dowels coming out of the foundation. It's all oiled. One of the things we learned was that this pour took us about 3 months to build. So usually formwork oil, you apply it, you pour, you strip it, right? But this form oil sat there for 3 months, and it was one of our challenges at the end of the day with the finish. But it's a pretty amazing feat just to stand up that first side of formwork. And we'd have carpenters waiting at the gate for the formwork. It was so hard to make, and that was feeding the job. And we'd get a tractor trailer, and it had 1 or 2 pieces of formwork on it. So just a really tough process to sustain.
So that form like dirt.
Yeah. That was one of the factors. That's the inside of the ring. So one of the factors of the decision of which side you stand up first was which side do you want to look better. And if you stood up the outside of the building first, you could control where it was much tighter. But if you left it there for 3 months, it would get dirty, and that would show on the finish, right? So there's the embeds. We shot everyone in, but the challenge with that is we have to put the rebar in there, and now you got dozens or hundreds of Nelson studs that are blocking out your 4-inch on center number 9s or number 11s. There's somebody asked about the sacrificial slab that we poured in the middle. There's some of the biggest box outs on the project. Again, none of this was handwork, all had to be craned in. It was a pretty sunset. That was one of the most congested pours. I think that picture has been printed out and put on some office walls. We negotiated every submittal, right? Every chair and every little piece that went into this to make sure that we were doing the right thing aesthetically. We had some challenges at the end of the project where we had to flatten all the tie wire down so that it wouldn't stick out and rust, but we still had to go back and repair maybe a dozen spots that were 12 pieces of tie wire out of all of this that ended up rusting. So a lot of attention to detail before we closed up the forms. There's two arches that hit the grade beam at the bottom. Epoxy coated rebar at some of the intersections was necessary because that's where the cracks were anticipated. Luckily, they haven't formed. So we think we're out of the woods on that one. There's a complicated shape that's that. So here we had to talk to the structural engineer. We hit this topic about the dowels coming out of the foundation, and we couldn't bend them, the dowels, every unique dowel with its own radius. So what we ended up doing was a pretty simple solution. We got the structural engineer to agree to change the spacing of the foundation dowels and squeeze them towards the inside of the arch so that when we spliced them, it would go on the outside of those dowels. And that gave us enough tolerance to deal with that smooth curve and not have all our foundation dowels button into our formwork. So more about the arches crossing. I showed you that in the mock-up, and the reinforcing design just got insanely complicated where the arches intersected. You can see it there. This is one of my favorite stories about the project. I think, yeah. So I already told you about the in-plane arch crossing and the out-of-plane arch crossing. And this is an example here where the green pour or the light green is an in-plane crossing, and that purple color is the out-of-plane crossing where they cross in front and behind of one another. Really big challenges, both of them. So there's the two placements. This one's about, I think, 30 to 35 feet tall, 150 feet long. There's some of these pours had over 100 pages of shop drawings for formwork and rebar for one pour. Terminators, I'm sure a lot of us have ran into terminators in our careers, but this was a unique application where if the arches crossed in front and behind one another, we had to implement the terminators that would hold those two arches from flopping out. So back to Herb, he convinced me to spend a lot of money to pour a, I don't know, 120 by 120, another sacrificial slab that was nice and flat right next to the building. And what Herb came up with, the reinforcing superintendent, was that he would take these two shapes, because we had all the points, and transpose them down on the slab and strike lines in between where all those bold green and blue lines are. And then he put 4-foot heavy duty horses up and built the rebar inside the lines. So here's a photo. These are the two pours I'm focused on here. They were what, pour 41 and another number, pour 36. So we built this. It took about 6 weeks to build one of these with 6 or 8 iron workers working 50 hours a week. But it was safer than having them shove bar up 60 feet above the ground. They didn't have to tie off because we're only 3 or 4 feet above the ground. Ready access to a crane. And then here's the crazy part. We picked it up and put it in the formwork. This one weighed 110,000 pounds, held together by tie wire. So we waited for a Saturday and we didn't tell anybody what we were doing. And this one took 13 hours from the time we picked it up to the time we let the crane go and put it in the formwork. So we did this probably 12.5 times for the biggest pours, because again, there was no way to stick build this rebar, but we laid out the pours on the slab, built the rebar inside of them, QC'd it all right there, and then ended up picking it up. Looking back on it now, we had a rigging engineer come up with some standard parameters for us, but we didn't engineer every pick. And I think even though we're only 6 or 8 years later, nowadays we would likely have to do that just because of the focus on making sure that type of thing was right.
So the grading points actually worked out? You didn't have to say, and adjust it all.
Well, there was one pour, I think it was this pick where something wasn't right. I think we had, I don't know how many connection points. Each yellow was 2 connection points. So maybe 15 connection points. And one of them was overloaded and a 30-foot long number 11 went like that and pulled out. So that was a scary day, but we put it back down. We readjusted all the rigging, picked it up, and that it worked out. All this false work was just to keep it from folding in half.
So probably point out the yellow there, those are Nelson super studs, or Epco super studs. Anybody's worked with those? And they were just like pieces of spaghetti as they look at this. They would just bend back and forth as we were looking this cage. But across the bottom, there's like 2 Epco super studs there that you can see. And it was pretty amazing just watching how all that worked together.
And it would move around and flop around, and we put it as close to the wall as we could, but then we had to pick it up, get it vertical, and walk the crane over with this on the hook so that we could put it in place. So it never held my breath for so long. So there you can see it getting plugged into the formwork. And again, back to Mike's point, you know, 1/4 to 1/2 inch formwork tolerances and making sure you built that rebar right inside the lines, or else you'd have 110,000 pounds on the hook and it wouldn't fit. So
This is where all those Nelson studs that are in the embed where you had to go through and make them all fit.
yeah, and on this pour, we put the embeds on the back of the cage and tried to get the location accurate enough so that when we put the rebar up, we could have carpenters get in there and shove them around and get them as close as we could. But as you can imagine, getting that embed in the right spot, either way, if you put it on the formwork or the rebar, it was tough either way. So there we go. We start splicing it together. That's the end of the 13 hours. So all those little tubes are braces that were holding the rebar to the formwork. And we left that night, each night, knowing that the rebar was now securely connected to the formwork. And then we come back, splice it all together, finish up the box outs that we left out. These box outs had to go in and then close up the formwork. And there's the pour. So pretty incredible process to get to that point. There's another 100,000 pound pick. That's an out of plane arch. So you had to get X, Y, Z all right with this cage. There it is in the formwork. So you get it, you get the theme. A little bit about the placement here, and I'm going to hit a few things a little bit quicker. But we ended up using 2 pump trucks and a splitter, a Y. So we'd pump into 4 ports at once. And that ended up, after some trial and error, being the best way, because if you had a pour that was 100 feet long, you couldn't expect the concrete to travel all the way to the other end. So we had to pick the quantity of ports so that the travel distance would let the concrete stay intact. So we'd use this port and pump up to here, and we'd measure it at 22 yards, 12 yards on this side, and then we'd change ports and pump 63 yards. And then change ports. So every color represents when we would unplug the pump truck and replug it into a new section of formwork. The big challenge was that this is a capped form. And like I showed you in the mock-up, you're not done pouring until you get that little corner full. The mix design was about the consistency. We'd say a runny milkshake. So it was almost liquid, and you couldn't force it into any area like you would a normal mix design because it would flow so heavily. So that's a picture of 2 pump trucks. There's the Y, and there's a guillotine, and there's a guillotine. So we were pumping 1, 2, 3, 4 ports at a time to top that pour out. So we built a sculpture. Pretty cool when it was just the concrete before we cluttered it up with everything else. Baker's PM came one day about a year after the concrete was done, and we had built all the walls and ceilings. And I swear he was almost in tears because we covered up some of this, and it was, yeah, it was all, you know, the intent, but we covered up some of the beautiful sculpture. So a couple other points I want to hit before we wrap up. The steel, I know we're at ACI, but I can't help myself. The steel was pretty crazy too. We had the structural embeds where the beams attached, but we also had these spring plate embeds, which Nathan mentioned briefly earlier, but it's another structural engineering innovation we don't think has ever been done anywhere. But before I get to that, the main members themselves, normally for steel members, we submit shops, we fabricate it, and then we erect it, right? On this project, we had to add in the surveying and as-builting into that process. So for every steel sequence, we had to pour the embed in, strip it, survey the embed, because it was impossible to get them exactly where we thought they were going to be. And you couldn't introduce a slotted connection big enough to handle that tolerance. So we more than doubled the normal fabrication time because we had to as-built every embed before we fabricated steel. Radial decking patterns was one of the more minor challenges that ended up smacking us in the face a little bit. And then the density we talked about, just negotiating the rebar cage with the embeds was very difficult. You could see every one of those is an embed plate that was probably 100 pounds with 8 Nelson studs that had to be integrated into that cage. And you could see we're sometimes successful with not having a radius on the embeds, and sometimes a little bit less successful where you'd have an inch or so of concrete that got in between. We had, I think, 500 embeds on this project, and we mislocated one of them. So there it is. Some pretty heavy duty post applied anchors there, you can imagine. We had some double-sided embeds where it wasn't a Nelson stud, but it was a solid rod. So we had to build the embeds into the cage because there's no way to install them afterwards. So those are the most problematic ones. Step beams, I think we've probably all been on a project with a step beam, but pretty complex here when you add the geometry of the building in with change in elevation in the beam. There's from below. There's our step. Radial beams that were really tough because typically we install something on a radius that's in a consistent elevation. We also had changing elevations here at our roof level. So this radial beam changed in all 3 dimensions, changed curves in all 3 dimensions. So again, something we kind of underestimated as we were getting into this project, the complexity of that steel. And put yourself in the fabricator's shoes in a fab shop somewhere, trying to figure out how to lay out and tell your welders how to attach all these parts of the beam together that change dimension in a compound curve. Pretty complicated stuff. So more about the steel. My friends at Columbus Steel Erectors would kill me if I came down here and didn't show you some of these pictures. Slotted connections, normally I think these are implemented for construction tolerance reasons. On this project, it was implemented for thermal movement reasons. So we had to get the bolts within a tolerance of the middle of that slot, or we had to cut the plate out and put a new one in after there was weight on the beam, because the structural engineer decided that the whole thing was going to expand and contract. They explained it like a bike tire. So the whole circle would get bigger when it was warm and smaller when it was cold. And so you had to account for expansion and contraction in all dimensions, inward and outward of the round building. And that's what this gap is for. This is a section of the outer arch and the beam that connects to it. And that's why those slots are so important. And we had to get the bolts right in the middle. But then also there's the slotted connections on the backside. There was these things called the spring plate, and the structural engineers realized that if the building expanded outwards, there was nothing that would make it go back inwards except for the thermal movement. And then when it went in, it might get stuck in, but it needed to go back to its original location. So they came up with this idea. It's either brilliant or crazy. I still haven't decided, but they have all these spring plates, which are high KSI steel that were vertical and connected. This thread is the concrete arch, and that's our slab on deck on the roof. I have a section here, I think, maybe in a moment, but the spring plate is connected to the arch here and the slab on deck on the other side here. And when the building expands outward, this 150 KSI steel pulls it back in. And when it expands inward, contracts inward, it pulls it back out. So there are a few hundred of these spring plates around the perimeter that help the building movement and contraction, which was also not the easiest thing to build. So the last few topics here, I know deflection in concrete structures is normal, but this was a little bit more extreme. And these are all the deflection calculations they showed us at every curtain wall mullion and creep and long-term, short-term, live load, dead load, all these different calculations that you structural engineers do. But on this project, what they told us was number 6 is the punchline there. They said, we think we got these calculations nailed. And then we got to the last note and they said, but really we have no idea. All right. So we said, oh, thank you guys. That's super helpful. So this is the exterior wall. Let me give you a context. That's the arch. That's our beam. And that's the roof slab. And Nathan and his team and our curtain wall supplier had to design the curtain wall to accommodate up to 5 inches of vertical deflection of these arches. So there's the concrete, there's the curtain wall. We had this really crazy boot detail, a silicone boot at the top that would accommodate 5 inches of movement, differential movement between the curtain wall and the concrete. And what we ended up doing was surveying, what is that, 8 points? And we were super, super concerned about this. So we surveyed over the 2 years following the concrete pours. We wanted to know exactly how much it deflected and compare it to the theory. The maximum planned or theory was about 5 inches. The maximum deflection that we encountered, I think, was about 1 1/8 inches. So it was about 1/4 to 1/5 of the worst case theoretical forecast. There's the spring plates. So these are embeds for the beams. All these embeds in between are for spring plates. So we had to figure out how to install those. There's the photo again. And it's hard to see, but those plates there connected to the arch and the slab and pulled them back and forth. So we also had to accommodate all the thermal stuff in a typical building around those spring plates. So all the insulation and the thermal break to the beam had to be accommodated as well.
Get measured the circumferential.
No, we figured the building wouldn't fall down because of this, but if it deflected too much, we were concerned. So we focused on that. And then one big surprise was that we worked closely with the structural engineer, but midway through the first couple wall pours, they said to us, you know that this building, we aren't convinced it'll stand up until it's built, the structure, 100%. And we said, well, wait a minute, we're not baking a cake. And they said, well, no, you gotta come up with a reshoring design so that when you strip a given pour, you can reshore it and you know that it won't fall down, just like the typical reshoring process. So midway through the first few pours, we had to quickly get out ahead of this and figure out which long spans had to be reshored, because the theory was the arch ring might collapse before the roof slab tied into it. The roof slab was a diaphragm that held it all together. So we had to figure out this reshoring design, and it doesn't look like much here, but tons of weight that were on these reshoring towers. That's a pretty hefty one there before we put that diaphragm on the roof that held it all together. ACI says, by the way, that the structural engineer of record has to design or at least tell the contractor it needs to be reshored. So we got pretty acquainted with that ACI section, you can imagine. So we're at ACI, super excited to be here. We wanted to focus on the structure, mainly the concrete, but just to touch on it. And if you're ever in Central Ohio, please go see it. If you're into construction, which we all are, or design, it's pretty amazing. Just a few final notes. The exterior wall, 100% custom. Company named Flynn out of Toronto was our partners, super capable. The biggest curtain wall firm in Canada. So if you're anywhere up there, look Flynn up if you're doing a project and you need somebody who can handle a pretty complex curtain wall system. We decided to put the curtain wall inboard of the arch so that it wasn't embedded in any of those box outs. But we had about a 1/2 inch tolerance where we had to get the concrete right so that the curtain wall would fit. And these diagonal mullions tracked the same line as the concrete, but they weren't actually embedded into it. So we worked with the design team to give ourselves as much tolerance as possible for that curtain wall system. All custom. So mullion profiles that we extruded for this project. Every mullion was studied in a high degree to make sure that it complemented the structure. There's an unrolled elevation of the curtain wall system, very, very detailed. And again, it mimicked the slopes. So we had to get that concrete right, or we couldn't wait to as-built and fabricate the curtain wall. We had to fabricate the curtain wall as we were building the structure. So we had to get the concrete right so that when our curtain wall arrived from Europe, it would fit. Again, heat mapping. We scanned every surface, all the beams to make sure the curtain wall would fit. I think we were out just over an inch in the worst spot, and we were able to make that work without any rework. There's our first few mullions going up, and a big sigh of relief to see that everything jived together. So it's a pretty incredible design, and it was certainly a challenging few years, but looking back on it in the rearview mirror and getting the opportunity to speak to people like you about it, just makes it all worth it, that we went through the struggles and the sleepless nights to get to the point where we could share it. So custom roof, custom finishes. There were awards that our carpenters won for the custom radial slat ceiling. So, everything you look at in this project was a pretty customized product. So that's it. Thank you for the opportunity.